The universe operates on a logic far stranger than we ever imagined. You are about to discover 35 cosmic phenomena that prove reality is not what it seems, a journey that will permanently alter your perception of space and time. By the end, you will see the cosmos not as a cold, empty void, but as a thinking, creative entity with its own mysterious rules. Why do particles instantly influence each other across galactic distances? And what invisible force is ripping the cosmos apart at an ever-increasing speed? What does it truly mean to live in a universe that constantly defies our expectations? Two particles, born from the same event and separated by unimaginable distances, remain locked in a silent, instantaneous dance. This is quantum entanglement, a phenomenon so strange it forced Albert Einstein to call it spooky action at a distance. He was deeply troubled by the idea that one particle could somehow know what was happening to its partner millions of light years away, a connection that seemed to violate the cosmic speed limit set by light itself. How could information travel faster than the fastest thing in the universe? The answer is that it does not travel at all. There is no signal, no beam of energy, no message passing between them. Instead, the two particles behave as a single, unified system no matter how far apart they are. When you measure the property of one, the other instantly assumes a corresponding state, as if they are two parts of a whole that was never truly split. This discovery was so radical that for decades physicists debated if it was even real, until a brilliant thinker named John Bell devised a way to test it. His mathematics proved that the universe really is this strange, that this spooky connection is a fundamental feature of reality, not a flaw in our theories. This shatters our classical understanding of space and time, suggesting that separateness might be an illusion and that a deeper, hidden layer of connection binds the cosmos. It is a profound clue that the universe thinks in terms of wholes, not just parts. And if this invisible web of connection exists, what other forces are silently shaping the cosmos from behind the curtain? This acceleration is not a gentle push but a relentless, growing force. The very fabric of space itself seems to be generating a repulsive gravity, an anti-gravity force that overwhelms the pull of every galaxy, star, and planet. For most of the 20th century, scientists were certain the universe's expansion was slowing down, that the collective gravity of all matter would eventually put the brakes on the Big Bang. Then, in the late 1990s, two independent teams, one led by Saul Perlmutter, made a shocking discovery. By observing the light from incredibly distant stellar explosions called Type 1, a supernova, which act as cosmic mile markers, they found these beacons were dimmer than expected. The only explanation was that the space between us and them had stretched more than anyone predicted. The universe was not just expanding, it was speeding up. This revelation was so profound it earned them the Nobel Prize and forced a complete rewrite of cosmology. The culprit was named dark energy, an invisible something that makes up about 68% of everything that exists. Yet we have no idea what it actually is. Is it a constant energy woven into the vacuum of space, as Einstein once proposed and then discarded? Or is it a dynamic field, a fifth fundamental force that has only now begun to dominate the cosmos? Its existence paints a startlingly lonely future. If this acceleration continues unchecked, distant galaxies will eventually be pushed beyond our cosmic horizon, their light forever too faint to reach us. The universe would end not with a bang, but in a vast, dark, and silent isolation, a big freeze where galaxy clusters become islands in an ever-widening emptiness. This invisible driver proves the cosmos is governed by rules we are only beginning to glimpse, rules that favor expansion over contraction and empty space over crowded gatherings. It is a fundamental preference written into the code of reality, a preference that leads us to another cosmic rule breaker, one that seems to play by its own set of physics entirely. Even as dark energy pushes the cosmos apart on the grandest scale, a mysterious force is pulling us together on another. Our galaxy, along with its neighbors, is caught in a relentless river of motion, all flowing toward a single, invisible point in the depths of space. This destination, hidden from our direct view by the thick dust and stars of the Milky Way's central bulge, is known as the Great Attractor. Its gravitational pull is so immense that it dictates the motion of hundreds of thousands of galaxies across a vast region of the universe. For a long time, this was a profound navigational mystery. How could our entire galactic neighborhood be on a collision course with something we could not see? The answer came from looking with different eyes, using radio telescopes that can pierce through the cosmic dust. What they revealed was not a single, monstrous object, but a gravitational focal point, a place where the normal distribution of matter is wildly concentrated. The sheer amount of gravity required to cause this great flow cannot be accounted for by the galaxies and gas we can observe there. It is as if we are all sliding down a slope toward a valley we know is there, but whose true depth and contents remain shrouded in fog. Astronomers like René Cron-Courtoueg have dedicated their careers to mapping this hidden geography, suggesting that the Great Attractor is likely a colossal supercluster of galaxies, its true mass amplified by immense amounts of dark matter. This unseen component acts as a gravitational anchor, weaving a web of influence that tugs on everything in its vicinity. It is a humbling reminder that what we see with our telescopes is only a fraction of what is actually there. The universe is filled with these invisible architects, building structures and directing traffic on a scale we are only beginning to comprehend. If such a powerful force can remain largely hidden in our own cosmic backyard, what other gravitational giants are waiting to be discovered in the deeper darkness? This grand mystery of invisible mass gives way to a phenomenon of pure, visible power, one that defies the very laws meant to contain it. Some signals in the cosmos are so powerful they can outshine entire galaxies, yet they last for less than a blink of an eye. These are fast radio bursts, immense flashes of energy that travel billions of light years to reach us, carrying more power in a single millisecond than our sun releases over many months. Their discovery was almost missed entirely, found by Duncan Lorimer and his student while sifting through old radio telescope data, a signal so bizarre it was initially dismissed as an instrument glitch. But it was real, a cosmic shout from the distant void. The mystery only deepens with each new detection. Some of these bursts are loners, a single, brilliant flash that never repeats, suggesting a catastrophic, one-time event like a neutron star collapsing into a black hole or two incredibly dense objects merging in a final, violent embrace. Others are repeat offenders, firing off signals again and again from the same patch of sky, which rules out a destructive source and points instead to a persistent engine, perhaps a highly magnetized neutron star known as a magnetar, capable of producing stellar tantrums of unimaginable ferocity. The extremes required to generate such a signal push the limits of known physics, leading some to ponder if we are listening to the byproduct of advanced technology, like massive interstellar power transmitters. While this is the least likely explanation, the very fact it can be seriously considered shows how deeply these bursts challenge our understanding. They are like cosmic lighthouses, their fleeting flashes briefly illuminating the vast, invisible clouds of material between galaxies, allowing us to map the universe's missing matter. Each new burst is a puzzle box, a brief, brilliant message that reminds us the universe is not only strange, but also remarkably loud, filled with sudden, explosive conversations we are only just beginning to overhear. And if space itself can ring with such violent, transient energy, what happens when that same fabric is stretched and warped into a perfect cosmic echo? The same cosmic collisions that create fleeting radio bursts also compose a deeper, more fundamental music. When two black holes, each containing the mass of dozens of suns, spiral into each other, they do not crash together in a flash of light. Instead, their immense gravity churns the very fabric of the cosmos, sending out ripples in space-time known as gravitational waves. These are not waves of light or sound, but literal distortions in the geometry of reality, stretching and squeezing everything in their path as they travel across the universe at the speed of light. For a century, this was just a beautiful mathematical prediction from Einstein's theory of general relativity, a ghost in the equations that seemed too faint to ever catch. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, did the impossible. Its twin detectors, separated by 1,800 miles, sensed a wobble in their lasers so minuscule it was smaller than the width of a single proton. That tiny tremor was the echo of two black holes merging over 1 billion light-years away. The universe had finally been heard. This discovery, which earned a Nobel Prize, did not just confirm a theory. It gave us an entirely new sense with which to explore the cosmos. Before this, our view of the universe was built entirely on light, from radio waves to gamma rays. Now we can listen to it. When LIGO and its European partner, Virgo, detect a passing wave, they are essentially hearing the final, frantic moments of a cosmic catastrophe, like the crescendo of a drumbeat from a collision we could never see. This new sense revealed its power spectacularly in 2017, when observatories detected waves from two neutron stars merging. Traditional telescopes around the world and in space immediately swiveled to the same patch of sky, capturing the brilliant glow of the resulting explosion. This event, multi-messenger astronomy in action, allowed scientists to witness the creation of heavy elements like gold and platinum, solving a long-standing mystery of where these materials come from. Theorist Kip Thorne called these waves the music of the cosmos, a symphony played on the strings of spacetime itself. Each new detection adds another note, helping us map the hidden population of black holes and test if Einstein's theory holds true under the most extreme gravity imaginable. How many more of these cosmic symphonies are vibrating through the universe, completely unnoticed? This profound new way of listening reveals a cosmos that is constantly in motion, a dynamic, writhing entity that communicates through the very shape of existence. Yet, for all this newfound cosmic noise, one of the most powerful mysteries in astronomy is defined by a profound and unsettling silence. The profound silence of the cosmos echoes far louder than any gravitational wave. With trillions of planets orbiting countless stars, the universe appears perfectly designed for life to flourish everywhere. Yet when we listen, we hear nothing but a vast and unnerving quiet. This is the heart of the Fermi Paradox, a puzzle framed by physicist Enrico Fermi over a simple lunch conversation when he asked a deceptively simple question. Where is everybody? The numbers are overwhelmingly on the side of existence. Frank Drake's famous equation breaks down the probability of finding other civilizations into a series of logical steps, from the number of stars with planets to the fraction where life emerges and eventually develops technology. By even the most conservative estimates, the Milky Way alone should be humming with thousands of intelligent societies. Our telescopes should be picking up their transmissions. Our sky should be dotted with their megastructures, yet every search has returned empty. This great silence forces us to confront unsettling possibilities. One is the Great Filter, a hypothetical barrier so difficult to overcome that it prevents almost all life from progressing to a galactic stage. This filter could lie in our past. Perhaps the jump from simple single-celled organisms to complex life is a cosmic fluke of near impossible odds. Or, more ominously, it could await us in our future, a point of technological maturity where every civilization inevitably discovers the means of its own destruction. Another possibility is that we are simply naive. Our searchers assume others communicate using radio waves or build visible structures, but a civilization millions of years more advanced might use technologies as far beyond our understanding as the internet is to smoke signals. They could be all around us, watching from higher dimensions or using forms of physics we have not yet discovered, rendering them invisible to our crude instruments. Or perhaps they are silent by choice, observing a strict cosmic quarantine to avoid interfering with fledgling species like our own. This eerie absence of evidence is itself a form of evidence, a cosmic lesson written in negative space. It suggests that the emergence of intelligence or its survival is governed by rules we have not yet decoded. The universe, for all its creative potential, might be a place where life is a fleeting whisper, or where intelligence learns to hide itself very, very well. This contemplative silence is shattered, however, by the arrival of a visitor from a place where no visitor should be. Even the universe's most reliable clocks sometimes skip a beat. Pulsars are the spinning corpses of massive stars, and they sweep beams of radiation across space with a regularity that rivals our most precise atomic clocks. They are the cosmic metronomes, ticking with such unwavering consistency that any tiny deviation in their rhythm stands out like a scream in a silent room. These timing anomalies are not errors but messages, encrypted signals pointing to extraordinary forces at work. A sudden, tiny glitch in the spin could be a starquake, a catastrophic cracking of the pulsar's incredibly dense crust, an event that would release more energy than 1,000,000 suns. A systematic, repeating wobble might betray the presence of an unseen planetary companion, its gentle gravitational tug subtly rocking the dead star. In fact, the very first planets ever discovered beyond our solar system were found orbiting a pulsar, a testament to the resilience of worlds forming from the ashes of a stellar cataclysm. Astronomer Jocelyn Bell Burnell, who first detected these pulsing signals as a graduate student, opened a window into one of the most extreme environments in nature. The anomalies she helped uncover continue to reveal secrets, hinting at the bizarre physics inside a neutron star, where a superfluid ocean of neutrons might suddenly unlock and transfer energy to the solid crust, causing it to spin faster in an instant. Some scientists even speculate that certain timing irregularities could be the signature of dark matter, vast clouds of invisible particles subtly dragging on the pulsar as it moves through space. Each tiny hiccup in the rhythm is a clue about matter pushed to its absolute limit, under pressures so immense that atoms are crushed into a soup of fundamental particles. These cosmic lighthouses do more than just guide us. They act as probes, their perfect rhythms allowing us to sense the invisible and the improbable. If even these paragons of regularity can behave so unpredictably, what does that say about the stability of the cosmos itself, especially when we look at the very largest structures we can see? While the cosmic web weaves galaxies into great clusters and filaments, it also carves out caverns of profound emptiness between them. These are the cosmic voids, regions of space so vast and so vacant they defy our very intuition about the universe. One of the largest, the Boötes void, spans an almost incomprehensible 330 million light-years. If our Milky Way were at its center, we would not have known other galaxies existed until the 1960s. The existence of such immense nothingness is a direct challenge to our models of how the universe structured itself after the Big Bang. Why did matter flock so decisively to certain areas, abandoning these colossal deserts? The answer lies in the faintest of beginnings, in quantum fluctuations from the first moments of time that were stretched to cosmic proportions by inflation. Where the primordial soup was ever so slightly denser, gravity got a head start, pulling in more and more matter over billions of years. Where it was thinner, gravity lost its grip, and those regions were left behind, expanding into the voids we see today. But to call a void empty is a misnomer. These regions are not perfect vacuums. They contain a few isolated galaxies, vast clouds of incredibly diffuse hydrogen gas, and most importantly, immense amounts of dark matter. Their true power, however, lies in their emptiness. Because there is so little gravitational pull inside them, voids expand faster than the universe average. They are cosmic pressure chambers, actively pushing the surrounding galaxies and clusters into the walls and filaments of the cosmic web. Cosmologists like Laura Mersini-Horton study these voids as laboratories for dark energy, as their rapid growth provides a unique measure of its repulsive force. The geometry of a void even bends light, acting as a makeshift gravitational lens in reverse, creating cold spots in the cosmic microwave background. This reveals a universe where emptiness is not passive, but an active, dynamic participant in shaping cosmic evolution. It values the void as much as the cluster, using absence to dictate the motion and fate of everything we see. If the prevalence of dark energy continues to accelerate this process, these voids will grow ever larger, ultimately determining the large-scale fate of the cosmos. But for every vast emptiness the universe creates, it also seems to generate a mysterious and overwhelming abundance. Deep within the chaotic heart of our own galaxy, a mysterious light refuses to be explained. The core of the Milky Way should be a place understood by predictable physics, dominated by the immense gravity of its central supermassive black hole and the frenetic energy of crowded star clusters. Yet, when scientists pointed the Fermi Gamma Ray Space Telescope toward this region, they found something baffling, a diffuse, powerful glow of gamma rays that simply should not be there. This is the galactic center excess, an energetic fog with no clear source. The initial and most thrilling hypothesis was that we were finally seeing the signature of dark matter. The idea is that when two hypothetical dark matter particles collide, they could annihilate each other in a flash of pure energy, producing the very gamma rays we observe. Physicists like Tracy Slatire have meticulously built models showing how certain types of these unseen particles could perfectly create this excess, a potential glimpse into the 85% of matter that has otherwise eluded all detection. But the cosmos rarely gives up its secrets so easily. A more conventional, though no less fascinating, explanation has gained traction: a vast, unseen population of millisecond pulsars. These are ancient neutron stars spinning hundreds of times per second, each one too faint to spot individually in the galactic crowd, but collectively creating the exact same diffuse glow. This is the core of the scientific debate. Is the signal evidence of a fundamental new particle, or just a previously unrecognized class of stellar corpses? The answer remains locked within the data, a reminder that our own galactic home is still a place of profound mystery. The very environment that makes this discovery possible, with its extreme densities and powerful energies, also complicates the interpretation, scattering light and masking true origins. This unresolved puzzle forces innovation, driving the development of new algorithms and future telescopes designed to tease apart the signal from the noise. It stands as a testament to a universe that hides its most profound secrets in plain sight, radiating from the very center of our celestial city. And if the fabric of space can conceal such energetic mysteries, what happens when time itself begins to behave strangely? The steady tick of a clock is one of humanity's oldest illusions. Time itself is a fluid medium, stretching and compressing under the influence of gravity. According to Einstein's revolutionary insight, a clock placed at sea level closer to Earth's mass will literally tick slower than an identical clock perched on a mountaintop. This is not a mechanical error, but a fundamental truth about the nature of reality, where gravity curves both space and the very passage of time. The effect is minuscule on our planetary scale, but it is undeniably real. Our global positioning systems are living proof. The atomic clocks aboard GPS satellites, orbiting high above Earth in a weaker gravitational field, run faster than their counterparts on the ground. If engineers did not deliberately slow down the satellite clocks to account for both this and their speed, the entire system would become useless within minutes, misplacing your location by several miles each day. This is relativity in action, a theory confirmed not just by technology but by decades of meticulous experiments. Physicists like Clifford will have tested these predictions to exquisite precision, finding that Einstein's equations describe our universe with stunning accuracy. The implications become truly cosmic when we consider a black hole. From a safe distance, you would watch a spacecraft fall toward the event horizon and see its clock slow to a crawl, its light redden and fade until it appears to freeze completely, a ghost ship trapped on the edge of forever. For the brave astronaut on board, however, time would pass normally, their clock ticking down the seconds until the inevitable. This is the heart of time dilation. There is no universal now. Your experience of time is uniquely your own, woven together with your motion and the local strength of gravity. It forces us to abandon the comforting idea of a single cosmic clock ticking the same for everyone. If time is so malleable, what does that mean for cause and effect, or for our understanding of the universe's singular beginning? The cosmos operates with a fluid sense of time, adapting its rhythm to local conditions. This realization that our view is limited by both time and space leads us directly to the edge of the visible universe, to a horizon that defines everything we can ever know. Our most precise measurements of cosmic expansion are telling two different stories. One story is written in the ancient light of the cosmic microwave background, the afterglow of the Big Bang. This relic radiation provides a snapshot of the infant universe, and from it, cosmologists can calculate how fast the cosmos should be expanding today. It gives us a very specific number for the Hubble constant, the rate of that expansion. Yet, when we look at the modern, nearby universe using the flicker of stars and the flash of supernova as our yardsticks, we get a different answer. The local universe appears to be expanding significantly faster. This stubborn mismatch is the Hubble tension, and it is more than a simple calibration error. It is a direct challenge to our standard model of cosmology, the very framework we use to understand the universe's history and fate. Could something fundamental be missing from our equations? Perhaps dark energy is not a constant force but one that has grown stronger over time, giving the expansion an unexpected boost. Or maybe the early universe contained additional types of radiation or exotic, fast-moving particles that subtly altered its initial conditions, throwing off our predictions. Astronomers like Wendy Friedman are pioneering new methods to break this deadlock. Her work focuses on a specific type of aging star, the red giant, which all reach the same peak brightness before they fade. These stars serve as a new class of standard candles, providing an independent check on the expansion rate that bypasses the old debates. The fact that the tension persists, even with these refined tools, is a thrilling indication that we are on the verge of a major discovery. The universe is subtly resisting our attempts to box it in with a single, elegant model. This disagreement over a single number reveals a crack in our understanding, a hint that the cosmos operates with a deeper, more complex set of rules than we have yet imagined. If we cannot even agree on how fast space is stretching, what other foundational truths about the universe's first moments might we have wrong? Even the faintest echo of creation holds a secret direction. Embedded within the cosmic microwave background, the oldest light in the universe, is a peculiar pattern that cosmologists have nicknamed the axis of evil. This is not a malevolent force, but a mysterious alignment of hot and cold spots that seems to define a preferred direction in the cosmos, a cosmic north that should not exist. The foundational assumption of modern cosmology, the cosmological principle, states that the universe is isotropic, meaning it should look the same in every direction, and homogeneous, with matter evenly distributed on the largest scales. The axis of evil directly challenges this core belief. It is as if you walked into a perfectly round room and found all the furniture subtly angled toward one specific wall. Researchers like Kate Land have meticulously studied this anomaly, searching for any error in the data or analysis that could create such an illusion. So far, it persists. If this alignment is real and not just a profound statistical fluke, it forces a radical rethink of our origin story. The prevailing theory of cosmic inflation, a period of fantastically rapid expansion in the universe's first moments, was designed to create a smooth and uniform cosmos. The axis of evil suggests that this process may have been imprinted with a direction from the very beginning, perhaps by a structure that existed before the Big Bang or by a fundamental feature of space-time we have not yet discovered. Why would the universe have a favorite axis? The answer might lie beyond our observable horizon, in realms whose influence we can only sense through such ghostly alignments. This anomaly is a humbling reminder that our maps of reality are still incomplete, and that the cosmos might be guided by a deeper, hidden geometry. From this vast, directional imprint on the universe's first light, we find that the largest structures are intimately connected to the smallest rules of existence. The universe maintains a delicate balance on the edge of a razor. At the heart of particle physics lies a number that seems impossibly small, the mass of the Higgs boson. This particle is responsible for giving all others their mass, a fundamental cornerstone of reality, yet its own weight is curiously light. The puzzle this creates is known as the hierarchy problem, and it reveals a shocking instability in our equations. The natural scale for gravity, the so-called Planck scale, is a mind-bending 10,000 trillion times larger than the scale of the weak nuclear force. Why is there such a monstrous gap between these two fundamental pillars of nature? In the quantum world, the mass of the Higgs should be constantly pushed upward by a storm of virtual particles, a chaotic sea of fleeting existence. For the Higgs to remain as light as we observe, these wild quantum corrections must cancel each other out with near-perfect, unbelievable precision. It is as if a pencil were balanced on its tip for billions of years, defying the slightest gust of wind. This degree of fine-tuning seems so unnatural that physicists are convinced something must be missing from our picture. Visionary thinkers like Nima Arkani have proposed breathtaking solutions. Perhaps new particles exist, partners to every known particle as predicted by a theory called supersymmetry, that perfectly counteract the quantum turbulence. Or maybe the force of gravity is not as weak as it seems, but is instead diluted, leaking into unseen extra dimensions of space that are curled up at microscopic scales. These are not just abstract ideas, they are necessary fixes for a model on the brink. The implications of this tuning are profound. If the Higgs mass were just a little heavier, the delicate processes that forge atoms in stars would fail. Complex structures from planets to people could never coalesce. This cosmic coincidence forces a fundamental question: is our universe uniquely engineered for life, or are we simply one lucky bubble in a vast multiverse, an island of stability in an infinite ocean of failed realities where the numbers did not line up? The hierarchy problem is a silent testament that the cosmos does not tolerate sloppiness, operating with a precision that demands a deeper, more elegant explanation. Such profound coincidences seem to be woven into the very fabric of existence, pointing toward an even greater cosmic alignment. This immense void in our understanding is known as the cosmological constant problem, and it represents the single greatest mismatch between theory and observation in all of science. The energy of empty space should not be empty at all. According to our best theories of the quantum world, the vacuum should be a seething, bubbling foam of virtual particles constantly flickering in and out of existence. This quantum activity should fill every cubic centimeter of space with a staggering amount of energy, a density so colossal it would have ripped the universe apart in its first fractions of a second. Yet when we measure the actual energy of the cosmos, the force we call dark energy, it is almost zero. The number predicted by quantum theory is a 1 followed by 120 zeros larger than the number we observe. This is not a small error, it is a chasm of incomprehension. Why is the energy of the vacuum so infinitesimally small, yet not perfectly zero? A value of zero would be strange, but mathematically elegant. This tiny positive value is a profound mystery. If it were just a little bit larger, the repulsive force would have been so powerful during the universe's infancy that galaxies, stars, and planets could never have clumped together from the primordial soup. The cosmos would be a featureless, expanding void. This incredible fine-tuning demands an explanation. The brilliant physicist Steven Weinberg and others have suggested a startling possibility: the anthropic principle. In a vast multiverse where every possible value of the cosmological constant exists, we naturally find ourselves in one of the rare, habitable bubbles where the number is just right for life to emerge. We are not here because the universe is special. The universe appears special because we are here to observe it. Alternatively, there could be a yet undiscovered symmetry or a dynamical mechanism in physics that forces the cosmological constant to cancel itself out to nearly nothing. This problem is the ultimate showdown between the two pillars of modern physics: the quantum world of the impossibly small and the gravitational cosmos of the impossibly large. Their refusal to agree on the energy of nothingness reveals a fundamental flaw in our understanding of reality. How does the universe achieve such a perfect and delicate balance? The answer remains one of the most sought-after prizes in theoretical physics. This deep mystery of empty space gives way to a puzzle about solid matter, specifically the baffling existence of stuff that should have completely vanished. The very first atoms tell a story that does not quite add up. In the universe's opening minutes, a frantic burst of nuclear fusion forged the primordial elements, a process we call Big Bang nucleosynthesis. Our calculations for the amounts of hydrogen and helium match the observations in ancient stars with stunning accuracy, a triumph for the Big Bang model. But there is a glaring exception: lithium. The predicted abundance of lithium-7, the universe's third lightest element, is about 3 times higher than what we actually measure in the oldest stellar populations. This is the lithium problem, a quiet but persistent crack in the foundation of our cosmic origin story. Why would lithium alone defy the predictions? One possibility is that our understanding of the nuclear physics in that seething infant universe is incomplete. Physicist Karsten Jadamzik has explored the idea of a resonant nuclear reaction, where certain atomic nuclei could have interacted with unexpected efficiency, essentially burning up the extra lithium as it formed. Another, more exotic, solution points to the invisible world. Could hypothetical particles of dark matter have been present in those first moments, decaying and releasing energy that altered the delicate nuclear chain reaction? Or is the answer written in the stars themselves? Perhaps these ancient stellar furnaces are far more efficient at destroying lithium over their long lifetimes than our models suggest, slowly depleting the primordial supply. This tiny discrepancy carries immense weight because it involves the very elements forged when the cosmos was only a few minutes old. Resolving it is not about correcting a minor detail. It is about getting the opening chapter of our universal history exactly right. The lithium problem is a humbling reminder that even our most successful theories are still approximations of a deeper, more complex reality. If we cannot fully account for the creation of a single, simple element, how can we hope to map all the matter the universe is supposed to contain? Our inventory of the cosmos contains a shocking deficit. When scientists tally all the ordinary matter, the protons and neutrons that make up stars, planets, and us, they find that a third of it has simply vanished from the nearby universe. This is the missing Baryons problem, a cosmic accounting error on a colossal scale. Our models of the Big Bang tell us precisely how much of this normal matter should exist, but when we look at galaxies and clusters, the numbers do not add up. The atoms are there, they must be, but they are not where we expected to find them. The leading suspect is a ghostly, searingly hot gas that floats in the vast spaces between galaxies, a diffuse fog known as the warm-hot intergalactic medium. This material is so tenuous and so hot that it does not glow with the familiar light of stars. It only betrays its presence by absorbing very specific colors from the light of distant cosmic beacons. Researchers like J. Michael Scholl have become master detectives in this search, using quasars as their flashlights. As the brilliant light of a quasar travels billions of light years to reach us, it passes through these invisible filaments of gas, which imprint a unique fingerprint of absorption lines on the spectrum. It is like analyzing a single sunbeam that has passed through a distant, invisible fog, revealing the composition of the fog itself. These observations confirm that the missing baryons are woven into the cosmic web, hiding in the million-degree filaments that connect galaxy clusters. Why has this matter been so difficult to see? The answer lies in the limits of our perception. This gas emits light mainly in the far ultraviolet and soft X-ray parts of the spectrum, a range that is largely blocked by our own atmosphere. It took space-based observatories to finally begin sensing this faint, pervasive glow. Solving this mystery is crucial. It is about completing the universe's basic ledger, proving we understand what the cosmos is made of on the most fundamental level. This hunt proves that the universe is a master of concealment, hiding immense amounts of its own substance in plain sight, not with dark matter, but with ordinary matter made extraordinary by its form and location. If so much of the universe's basic building blocks can evade our notice for so long, what other colossal structures might be hiding just beyond the edge of our vision? The scale of the Boots void is almost impossible to grasp. This cavern of near-nothingness stretches over 330 million light-years, a volume of space so empty that if our galaxy were placed at its center, the nearest wall of the cosmic web would be impossibly far away, a lonely island in an ocean of darkness. Its discovery by astronomer Robert Kirshner and his team in the 1980s was a shock to the field of cosmology. How could the universe, which supposedly formed through the gradual clumping of matter, produce a desert of such staggering proportions? The void is not a perfect vacuum, of course. A sparse collection of about 60 galaxies has been identified within its expanse, but that number is shockingly small. In a region of that size, you would expect to find thousands. The existence of boots forces us to reconsider the very seeds of cosmic structure. It likely grew from a region in the infant universe that was profoundly underdense, a slight deficit in the primordial quantum foam that was then stretched to a colossal scale by inflation. In this scenario, gravity was the sculptor of absence. While matter was busy pulling itself together into galaxies and clusters elsewhere, here it was flowing outward, draining away toward the denser regions that border the void. This makes these empty regions powerful probes for the invisible forces shaping our cosmos. The way galaxies are distributed around the edges of the boot's void, and the subtle motions they exhibit, tell a story about the gravitational tug of dark matter, the unseen scaffolding that guides their flow. Furthermore, because there is so little matter inside them to provide gravitational resistance, voids like boots expand faster than the universe average, providing a unique measure of dark energy's repulsive push. They are not passive holes, but active players in cosmic evolution, their growth helping to shape the great filamentary walls we see. The very existence of such a vast emptiness challenges the cosmological principle, the idea that the universe is roughly the same everywhere when viewed on a large enough scale. Is the Boots void a rare statistical fluke, or a sign that the distribution of matter is far more complex and textured than we imagined? This profound emptiness, however, stands in stark contrast to one of the most colossal assemblages of matter ever discovered. The vast emptiness of the Boots void is not the universe's only architectural marvel. Looming in the opposite direction is a structure of such immense density and scale, it seems to defy the very laws of cosmic construction. This is the Sloan Great Wall, a colossal filament of galaxies stretching over 1.4 billion light-years, one of the largest single structures we have ever identified. To cross this wall at the speed of light would take a journey longer than a tenth of the current age of the universe. Its discovery was made possible by the Sloan Digital Sky Survey, a monumental project that systematically mapped the three-dimensional positions of millions of galaxies, revealing the true skeleton of the cosmos. What it showed was a web far more complex and lumpy than anyone had anticipated. The existence of such a titanic structure poses a direct challenge to the cosmological principle, the foundational idea that on the largest scales, the universe should appear smooth and uniform. How could gravity, working with only the 14 billion years since the Big Bang, have possibly assembled something so enormous? Cosmologists like J. Richard Gott have studied this Great Wall, using its staggering dimensions to test the limits of our models for cosmic structure formation. It seems the tiny, quantum seeds of irregularity from the universe's first moments were perfectly primed to grow into these vast, interconnected highways of galaxies, woven together by the invisible threads of dark matter. The Sloan Great Wall is a humbling reminder that our maps are still being drawn, and that the cosmos prefers intricate texture over bland uniformity. With every new, deeper survey, astronomers ask if this is truly the upper limit, or if we will soon discover structures that make even this wall seem small. This discovery of immense, coherent motion in the architecture of space leads directly to a mystery about motion on a far more intimate and bizarre scale. Even our own galactic home floats within a cosmic bubble of nothingness. This is the KBC void, a region of space 2 billion light-years across where the density of galaxies is significantly lower than the cosmic average. Named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, This local underdensity is not just an interesting feature of our neighborhood, it is a potential key to unlocking one of cosmology's greatest puzzles. If we are living inside a vast, relatively empty bubble, our measurements of the universe's expansion rate are fundamentally skewed. The galaxies we use as local yardsticks are not just flying apart from us due to the universe's expansion. They are also being gently tugged outward by the gravitational influence of the denser walls of matter that surround our void. From our vantage point inside this bubble, it looks like the universe is expanding faster than it actually is on a global scale. This could be the simple, elegant explanation for the Hubble tension. The discrepancy between the local and early universe measurements might not be a flaw in our physics, but a flaw in our perspective. We are like sailors trying to measure the ocean's current while floating in a massive, slow-moving eddy. Our local readings are real, but they are not representative of the entire cosmic sea. Amy Barger's work in mapping large-scale structure has been crucial in characterizing this void, revealing that our cosmic address is far from average. This phenomenon, known as cosmic variance, suggests that an observer in a dense galaxy cluster would measure a different Hubble constant than we do. How many other such bubbles and dense regions are there, each giving their inhabitants a different story about the universe's expansion? The KBC void is a humbling reminder that we must always account for our own place in the cosmos, and that what we see is not always the full universal truth. This local emptiness forces us to look beyond our immediate surroundings, to the very first light that ever traveled through the cosmos for a clearer view. That ancient glow from the universe's infancy holds a distinct and chilling cold spot. In the map of the cosmic microwave background, one region stands out as profoundly colder than its surroundings, a vast patch of sky that resists all simple explanations. This is not a minor temperature fluctuation, but a colossal anomaly so large and so cold that its probability of occurring by random chance is incredibly small. The most conventional explanation is that it is simply a statistical fluke, a rare wrinkle in the fabric of the primordial cosmos. Yet, its sheer size and stark temperature drop have compelled scientists to consider far more radical ideas. One compelling theory points to a supervoid, an immense region of space with a startlingly low density of galaxies. If such a void existed along our line of sight to the cold spot, the light from the cosmic microwave background would have to climb out of this gravitational well, losing energy and stretching to longer, cooler wavelengths in a process known as the integrated Sachs-Wolf effect. Initial observations did find a notable underdensity of galaxies in that direction, but the scale of the void required to create such a pronounced cold spot is astronomically extreme, pushing the limits of what we believe is structurally possible in our universe. This has led theorists like Laura Mersini-Houghton to propose a truly breathtaking alternative, that the cold spot is a cosmic bruise, the imprint of a collision with another universe in the vast multiverse. In this scenario, the energy drain from that primordial interaction left a permanent cold scar on our sky. Such an idea directly challenges the standard inflationary paradigm, which was designed to create a smooth and uniform cosmos. Why would one part of the newborn universe be so different? The cold spot forces us to question if our universe's birth was truly a singular, isolated event, or if it was shaped by external forces we are only now learning to detect. It is a fossil from a time before time, a relic that could rewrite our entire cosmic origin story. As we study these immense imprints on the fabric of space, we must also consider the invisible forces that move through it, the vast magnetic fields that weave between the galaxies. The emptiness between galaxies is not truly empty, but threaded with invisible lines of force. intergalactic magnetic fields, faint yet unimaginably vast, weave through the cosmic void, creating a ghostly magnetism on the largest of scales. These fields are incredibly weak, millions of times weaker than a common refrigerator magnet, but their influence stretches across billions of light years. They act as invisible guides for cosmic rays, the high-energy particles that scream across the universe, bending their paths and obscuring their origins. They may even play a subtle role in shaping the great flows of gas that eventually collapse to form new galaxies. The great mystery is where they came from. Are these fields primordial, a fossil imprint from the universe's very first moments, generated during the violent period of inflation when space itself expanded faster than light? Physicists like Ruth Jura explore this profound possibility, that the seeds of today's cosmic magnetism were planted in that initial burst of creation. Alternatively, they could be a later addition, blown out into the void by powerful astrophysical engines like the supermassive black holes at the centers of active galaxies, which can spew magnetized plasma across intergalactic space. To probe these invisible fields, scientists use ingenious indirect methods. When high-energy gamma rays travel across the universe, they can collide with lower-energy light, and the presence of a magnetic field subtly alters the outcome of this collision. By studying the gamma rays that reach telescopes like Fermi, astronomers can trace the hidden magnetic landscape of the cosmic web. This discovery reveals a cosmos that is not only held together by gravity, but is also magnetically active, a universe crackling with silent, pervasive energy. What other unseen forces are guiding the evolution of galaxies from the darkness? This magnetic web connects everything, even to the most ethereal and elusive visitors from deep space. These cosmic phantoms slip through planets and people without a trace. Neutrinos are the universe's ultimate ghosts, subatomic particles so ethereal that they can pass through a light year of solid lead without a single interaction. Right now, as you listen, billions of them are streaming through your body every second, a silent, unstoppable rain from the sun, from distant supernova, and from the depths of our own planet. Their defining characteristic is this profound elusiveness, a refusal to engage with the ordinary matter that makes up our world. For a long time, we thought they were completely massless, traveling at the speed of light without a care. Then a stunning discovery turned that idea on its head. Experiments like the colossal Super Kamiok and in Japan revealed that neutrinos oscillate, seamlessly changing their identity between three different types as they travel. This chameleon-like behavior is only possible if they possess a tiny but real mass. This was a monumental discovery, one that forced a revision of the standard model of particle physics, our most complete catalog of the universe's building blocks. But it raised an even deeper question: why do they have mass at all, and where does this infinitesimal weight come from? The answer might lie in new, fundamental physics, perhaps involving massive, unseen partner particles. Their ghostly nature is precisely what makes them such powerful cosmic messengers. When a star explodes as a supernova, its core collapses, and the resulting burst of neutrinos is the first signal to escape, carrying news of the cataclysm outward. For supernova 1987, detectors on Earth registered a handful of these particles hours before the visible light from the explosion reached our telescopes, proving they travel at nearly the speed of light and giving us a direct glimpse into the heart of a dying star. Massive cubic kilometer detectors buried deep in Antarctic ice, like the Ice Cube Observatory, use the planet itself as a filter, waiting for the incredibly rare occasion a neutrino does collide with an atom, releasing a faint, telltale blue flash. These detectors are not just observing the sky, they are performing a kind of cosmic tomography, using these penetrating particles to see inside the most violent and energetic objects, like the jets of active black holes. From the first moments of the Big Bang, neutrinos played a crucial role, their slight mass and incredible speed influencing how the primordial soup of particles clumped together to form the first seeds of galaxies and the cosmic web we see today. They are a constant, pervasive, and formative presence, a reminder that the cosmos is built as much from the intangible and the unseen as it is from the stars and planets we can easily observe. Their silent journey through everything challenges our perception of solidity, proving that even the most familiar objects are, at a fundamental level, mostly empty space traversed by phantoms. This ability of the universe to bend and focus even the most elusive particles leads us directly to one of its most useful tools, the cosmic magnifying glass. Gravity's cosmic magnifying glass sometimes reveals more than we bargained for. When the light from a distant galaxy travels toward us, its path is bent and warped by the immense gravity of a massive object in the foreground, like a galaxy cluster. This effect, predicted by Einstein, can stretch the background galaxy's image into brilliant arcs or even split it into multiple, identical mirages. It is a perfect demonstration of mass-curving spacetime. Yet, time and again, astronomers observe a lensing effect that is far too powerful. The gravity required to warp the light so severely simply cannot be accounted for by all the visible stars and gas in the foreground cluster. The only logical conclusion is that an immense amount of invisible matter is there, providing the extra gravitational muscle. This is one of the most direct proofs of dark matter's existence. A legendary example is the Bullet Cluster, where two galaxy clusters collided in a cosmic wreck of unimaginable scale. During the collision, the clouds of hot gas, the cluster's normal matter, slammed into each other and slowed down. But the dark matter, which does not interact with anything except through gravity, sailed right through the crash. By meticulously mapping the gravitational lensing, scientists like Douglas Clow could literally pinpoint where the bulk of the mass had ended up. The lensing showed the mass was not with the visible gas, but in two separate clouds far ahead of it. Dark matter had been caught in the act, revealing itself as a real, tangible component of the universe, separate from everything we can see. These anomalies do more than just confirm dark matter, they help us map its invisible architecture. By studying how the light is distorted, we can create a detailed distribution of the unseen mass, revealing the hidden skeleton of the cosmic web. Sometimes the anomalies are even stranger, producing perfect Einstein rings or strangely symmetrical multiple images. These exquisite patterns hint at the possibility of other exotic objects within the lens, like a swarm of primordial black holes left over from the Big Bang, or even the subtle influence of cosmic strings, theoretical defects in the fabric of spacetime. Each distorted image is a weight scale for the cosmos, allowing us to indirectly weigh entire galaxies and measure the geometry of the universe itself. This creative bending of light proves that the cosmos uses its own gravity as a tool for revelation, twisting the paths of photons to illuminate the darkness. But what happens when the universe's most reliable beacons suddenly and mysteriously go dark? Even our most trusted cosmic yardsticks can sometimes lie. The universe relies on standard candles, certain types of stars and stellar explosions that burn with a known, predictable brightness, allowing astronomers to calculate vast distances across space. Cepheid variable stars pulse with a rhythm directly tied to their true luminosity, while Type 1, a supernova, the thermonuclear detonations of white dwarf stars, are thought to always explode at the same peak brightness. These are the foundation stones upon which we've built our cosmic distance ladder, the sequence of measurements that tells us how far away galaxies are and how fast the universe is expanding. But what happens when these candles flicker unexpectedly? Some supernovae appear dimmer or brighter than the standard model predicts, a discrepancy that can throw off distance calculations by millions of light years. This is not a minor issue. It strikes directly at the heart of the Hubble tension, the ongoing debate over the universe's expansion rate. If our candles are flawed, our entire map of the cosmos could be skewed. Nobel laureate Adam Rees and his team spend their careers in a relentless pursuit of precision, meticulously observing these celestial beacons with the Hubble and James Webb Space Telescopes, searching for the subtle biases that might explain the inconsistencies. Why would a standard candle fail? The answer lies in the rich diversity of cosmic life. A supernova's brightness might be affected by the chemical makeup or metallicity of its parent star. Its age or the complex dynamics of its binary star system could alter the conditions of its final explosion. Each of these variables introduces a potential error, a small crack in the foundation of our measurements. This forces a continuous cycle of refinement, where every anomalous, too bright or too dim supernova is not a failure but a lesson. It teaches us that the universe abhors simple uniformity. These failing candles are a profound reminder that nature prefers a spectrum of possibilities to a single, neat rule. They compel us to look deeper, to calibrate our tools with ever greater care, and to acknowledge that the cosmos will always be more complex than our models. This challenge in perfectly calibrating our view of the universe makes the discovery of a true cosmic twin all the more startling. A single brilliant mind can appear in two places at once. Deep in the constellation Ursa Major, a quasar blazes with the light of 1 trillion suns, its brilliance powered by a voracious supermassive black hole. Yet, when astronomers first trained their telescopes on it, they saw not one, but two identical copies shining side by side. This is the twin quasar, the first confirmed gravitational lens, where a massive foreground galaxy warps the fabric of spacetime so profoundly that it splits the distant quasar's light into a perfect cosmic mirage. The two images we see are not separate objects, but a single entity whose light has traveled two different paths around the lensing galaxy, a journey that takes slightly longer for one image than the other. By patiently monitoring the flickers and flares of the quasar, scientists like Rudolf Scheil discovered a time delay between the twins. When the quasar's core brightens, that flash appears in one image weeks before it shows up in the other. This delay is not just a curiosity, it is a precision tool. By measuring the difference in the light travel time and knowing the geometry of the system, astronomers can perform a direct cosmic measurement, calculating the scale of the universe and providing an independent check on the Hubble constant. But the twin quasar holds deeper mysteries. Sometimes the two images vary in brightness in ways that do not quite match, as if one twin is flickering independently. The culprit is an even finer level of cosmic trickery called microlensing. Individual stars within the lensing galaxy, drifting through the line of sight, act as tiny secondary lenses, their gravity briefly magnifying one image more than the other. These subtle fluctuations are more than just noise, they are a powerful probe. By studying them, scientists can map the invisible population of compact objects and even dark matter clumps within the lensing galaxy, structures far too faint to see by any other means. The twin quasar is a masterclass in cosmic deception, proving that gravity is the ultimate illusionist, capable of creating multiple views of a single reality. It raises a tantalizing question. How many other multiply-imaged monsters are hiding in the sky, their true nature masked by the warping of light? Each new lensed system discovered adds another data point, helping us refine our models of dark matter and the universe's expansion. This cosmic mirror reveals that the universe is not above using a little sleight of hand. bending the rules of perception to show us something new about its deepest workings. From these delicate gravitational illusions, we turn to the most violent and unambiguous explosions the cosmos can produce. The brilliance of a dying star can sometimes defy all expectation. While a typical supernova outshines its entire galaxy for a few brief weeks, a superluminous supernova can blaze with the power of hundreds, a stellar catastrophe of almost unimaginable ferocity. These are not merely bigger explosions, they are a different kind of stellar death entirely, powered by engines that push the known laws of physics to their absolute limit. One leading theory points to the birth of a magnetar, a neutron star spinning hundreds of times per second and armed with a magnetic field so powerful it could erase a credit card from half the distance to the moon. As this newborn cosmic dynamo spins down, it dumps a colossal wave of energy into the expanding shell of the supernova, causing it to glow with an intensity that normal supernova could never achieve. Another possibility is even more cataclysmic, the pair instability supernova. This occurs in stars so massive, with cores above 130 solar masses, that the sheer heat inside sparks a runaway nuclear reaction. The energy produced creates matter and antimatter pairs, causing a catastrophic drop in pressure that makes the star's core collapse not outward but inward. The result is a thermonuclear bomb that utterly annihilates the star, leaving behind no black hole, no neutron star, only scattered stardust and a light curve that scars the cosmos. Astronomers like Avishai Galyam meticulously dissect the light from these events, their unique spectral fingerprints revealing the specific elements forged in the blast and pointing toward the true trigger. Automated sky surveys like the Palomar Transient Factory are crucial in this hunt, scanning the heavens night after night to catch these rare, brilliant flashes the moment they appear. Why does the universe need such excessively violent stellar deaths? The answer may lie in our cosmic past. In the early universe, the first stars were behemoths, and pair instability supernova may have been a common finale. These extraordinary explosions would have been primary forges for the first heavy elements, seeding the pristine cosmos with the raw materials for future planets and life. Each detection is a direct window into the most extreme conditions matter can endure, a laboratory for nucleosynthesis operating at its absolute upper limit. They reveal a cosmos that is not just powerful but flamboyantly so, capable of stellar endings so bright they momentarily eclipse the combined light of billions of stars. This preference for such dramatic finales makes the universe's embrace of absolute darkness all the more perplexing. Our cosmic horizon may not be the final boundary after all. While the universe expands in all directions, something strange is happening on the very largest scales we can measure. Vast clusters of galaxies, each containing thousands of stellar systems, are not merely drifting apart with the cosmic flow. They appear to be moving together, swept along in a coherent, silent river toward a single point in the depths of space, a motion we call the dark flow. This is not the gentle tug of the Great Attractor, but something far grander and more mysterious, a current that seems to originate from beyond the edge of everything we can see. The discovery was made by a team led by cosmologist Alexander Kashlinsky, who analyzed the subtle patterns in the cosmic microwave background, the oldest light in the universe. They were looking for the imprint of galaxy clusters moving through this relic radiation, and what they found was staggering. Hundreds of clusters, spanning billions of light years, were all streaming in the same direction at astonishing speeds, a coordinated motion that the combined gravity of every known structure in the observable universe is utterly incapable of producing. So what could possibly be pulling them? The force required is so immense that the only plausible source lies beyond our cosmic horizon, in a realm whose light has not had time to reach us since the Big Bang. One breathtaking possibility is that the gravitational tug comes from a vastly different region of spacetime, perhaps a neighboring universe in an infinite multiverse, whose mass is unevenly distributed and is exerting a pull on our entire local cosmos. Another idea points to a pre-inflationary structure, a relic from the universe's first fleeting moments that was stretched to cosmic proportions but never fully smoothed out. Why would the cosmos exhibit this strange preference for a single direction? The dark flow directly challenges the cosmological principle, the foundational idea that the universe is isotropic and looks the same in every direction. If this flow is real, it means that on the very largest scales, the universe is not uniform at all, but has a texture and a directionality written into its fabric. This controversial phenomenon reminds us that our view is limited, that our observable universe might be just one small province in a far vaster and more complex metacosmos. The dark flow is a ghostly current, a hint that our island universe is not an island, but is connected to something else, something entirely beyond our current comprehension. This mysterious, large-scale motion suggests a cosmos where even the grandest motions are part of a deeper, hidden harmony. The same gravitational force that creates silent ripples in spacetime also composes a subtle, celestial music. Across our solar system and beyond, planets and moons often fall into rhythmic orbital dances, their years and months locked together in perfect whole number ratios, like notes in a cosmic chord. This is the music of the spheres, a mathematical harmony written by gravity itself. Consider the 3 inner moons of Jupiter. For every single orbit completed by the outermost Ganymede, the middle moon Europa completes exactly 2, and the innermost volcanic Io completes 4. This 1 to 2 to 4 resonance is a gravitational masterpiece, a repeating cycle that keeps their path stable and predictable over billions of years. These resonances are not accidents, but the natural end product of gravitational tugs over immense timescales. As these bodies gently pulled on each other, they gradually nudged one another into orbits where their gravitational influences became rhythmic and reinforcing, rather than chaotic and disruptive. This minimizes the risk of catastrophic collisions, creating a stable, long-lasting system. The late, great astronomer Carl Sagan saw this not as a mere curiosity, but as a profound reflection of the universal laws that govern everything, from the smallest atom to the largest galaxy cluster. It is a physical manifestation of the mathematical beauty woven into the fabric of reality. From the resonant gaps in Saturn's rings to the synchronized dance of planets around distant stars, these harmonic relationships reveal a cosmos that values order and pattern. It is a universe that, in its own slow and grand way, keeps a beat. Yet, for every harmonious system gravity composes, it also creates configurations of breathtaking chaos. Chaos is the universe's unwritten physics. The vast spaces between the stars and galaxies are not serene voids but seething oceans of turbulent gas and plasma, churning with energies that dwarf any storm on Earth. This is cosmic turbulence, a chaotic dance that moves energy from the largest scales down to the smallest, shaping the very evolution of galaxies. When a star explodes as a supernova, its blast wave slams into the surrounding interstellar medium like a titanic hammer, stirring it into a frenzy of ripples and eddies that can persist for millions of years. The colossal collisions of entire galaxies whip the gas within them into a froth, while the jets from active supermassive black holes act as cosmic mixers, injecting unimaginable power into the intergalactic medium. These are the engines of chaos, generating turbulent flows that span light years. But how is this frenzy sustained, and what are its rules? Physicists like Stanislav Boldarev explore the complex physics of magnetohydrodynamic turbulence, where magnetic fields and ionized gas become entangled in a single, fluid system. Their work reveals a universal process where large worlds break down into smaller and smaller worlds, efficiently dissipating energy in a cosmic cascade. This turbulence is not random noise, it is a fundamental force of creation. It governs the birth of stars by stirring clouds of gas, creating dense knots that can collapse under their own gravity. It amplifies weak magnetic fields, twisting and stretching them until they become powerful cosmic magnets. It scatters and accelerates cosmic rays, the high-energy particles that streak across the galaxy. Why would a cosmos built on mathematical precision rely so heavily on such apparent disorder? The answer is that turbulence is not the opposite of order, but its partner. It is the dynamic, efficient mechanism the universe uses to transfer energy, to mix elements, and to build complex structures out of raw chaos. This intricate balance reminds us that the cosmos is a living, breathing entity, constantly in flux. For all this violent motion, there exists a profound and contrasting stillness, a place where the universe's chaotic energy is frozen in an instant of perfect, timeless calm. Our sun's fiery temper can fall into a profound silence. During its 11-year cycle, the star enters a solar minimum, a period of relative calm with few sunspots and diminished flares. But history reveals these quiet phases can sometimes deepen into something far more extreme, a grand minimum like the Maunder minimum of the 17th century. For roughly 70 years, from around 1645 to 1715, sunspots virtually vanished from the solar surface. This prolonged hush coincided with the deepest chill of the Little Ice Age, a time when frost fairs were held on the frozen River Thames and glaciers advanced across Europe. The connection is not a simple one. A slight dip in the sun's total energy output alone cannot fully explain such a significant climatic shift. Researchers like Joanna Haig investigate the subtler mechanisms, proposing that the sun's altered ultraviolet radiation during a minimum can reshape the chemistry and dynamics of our planet's upper atmosphere, triggering a cascade of effects that ultimately cool the surface below. Why does the sun's powerful magnetic dynamo, the engine of its cycles, occasionally stumble into such a deep and prolonged slumber? The answer lies in the complex fluid dynamics of the sun's interior, where vast rivers of plasma churn and twist to generate magnetic fields. A grand minimum may occur when these flows become disorganized, temporarily suppressing the creation of sunspots. This solar stillness does more than just affect our climate. It fundamentally changes the nature of interplanetary space. The heliosphere, the vast protective bubble of solar wind that surrounds our solar system, shrinks and weakens. With the sun's magnetic shield diminished, more high-energy cosmic rays from distant galaxies can penetrate inward, potentially increasing cloud cover on Earth and affecting the chemistry of other planetary atmospheres. The quiet sun is a humbling reminder that our local star, the most familiar object in our sky, possesses hidden rhythms and moods we are only beginning to decipher. Its capacity for such deep calm proves that the cosmos balances its most violent outbursts with periods of profound tranquility. And if our own sun can fall so silent, what other forms of cosmic noise might we be missing in the vastness of space? Our motion through the cosmos is written in the universe's first light. The cosmic microwave background is not a perfectly uniform glow. It is slightly warmer in one direction of the sky and cooler in the opposite, a pattern known as the dipole anisotropy. This is the ultimate cosmic speedometer, created as our solar system moves at over 1 million miles per hour relative to this primordial radiation. Just as you feel a wind against your face when you run, we are plowing through the faint afterglow of the Big Bang, and it creates a hot spot ahead of us and a cold spot behind. This measurement is exquisitely precise, and for the most part it aligns perfectly with our local motion, the Sun's journey around the galactic center, and the Milky Way's own trajectory. Yet a subtle mystery lingers. Some analyses, scrutinized by cosmologists like David Spergel, suggest there might be a tiny, unexplained excess in this signal, a whisper of an additional component that cannot be accounted for by our local movements alone. Could a small part of this dipole be primordial, a fossil imprint from the universe's violent birth, a fundamental lopsidedness baked into space-time itself? This would directly challenge the cosmological principle, the idea that the universe is fundamentally the same in all directions. The very fact that we can use this ancient light as a stationary reference frame is a profound cosmic gift, a fixed backdrop against which we can measure all other motions. Why is our solar system's velocity so neatly aligned with this universal rest frame? It reveals a deep connection between our local galactic neighborhood and the immense cosmic flows that shape the universe's large-scale structure. We are not privileged observers at a standstill. We are participants in a grand, universal dance carried along by gravity's currents. This fundamental motion, measured against the oldest signal we can detect, primes us to question if there are even larger, more mysterious alignments woven into the fabric of everything. This proposed chasm in the constellation Eridanus is so vast it could be the source of the Great Cold Spot itself. The Eridanus Supervoid is an underdensity of staggering proportions, a region where galaxies are so scarce its sheer size pushes the boundaries of what our cosmological models deem possible. If confirmed, this supervoid would rank among the largest structures ever discovered, a true titan of nothingness. Astronomers like István Sapudi have painstakingly mapped this region using galaxy surveys, piecing together a portrait of this immense cosmic desert. The connection to the cold spot lies in a subtle but powerful gravitational effect. As the ancient photons of the cosmic microwave background travel across the universe, they must climb in and out of the gravitational wells created by matter. When a photon enters a dense region, it gains energy, making that part of the sky appear slightly warmer. But when it climbs out of a void, a region of missing gravity, it loses energy. The Eridanus Supervoid, with its profound lack of matter, would act as a vast, gentle hill. Photons exiting this region would be stretched to longer, cooler wavelengths, imprinting a distinct cold patch on the sky exactly where we see it. This is the integrated Sachs-Wolf effect in action, a direct imprint of cosmic structure on the first light, but the theory faces a formidable challenge. The void needed to create a cold spot this pronounced would have to be astronomically large, perhaps larger than our models of structure formation can comfortably accommodate. How common are such supervoids? If they are exceedingly rare, then the Eridanus void might be a perfect, if unlikely, explanation. If they are more common, it would force a radical rethink of how emptiness evolves in our universe. This great emptiness demonstrates that nothingness is not passive. A void is not merely an absence, it is a physical entity with its own gravitational personality, capable of leaving a permanent chill on the oldest light we can see. The Eridanus Supervoid is a cosmic blank space that somehow speaks volumes, proving that emptiness can shape our perception of the cosmos as powerfully as any star. This profound vacancy stands in stark opposition to the universe's incredible talent for creating overwhelming abundance. The light from a cosmic beacon carries the ghostly imprint of everything it has ever passed through. When astronomers point their telescopes at a quasar, the brilliant core of a distant galaxy, they do not see a pure, clean spectrum of light. Instead, they find it scarred by a veritable forest of dark absorption lines, a phenomenon known as the Lyman-Alpha forest. Each of these lines is a cosmic road sign, marking the presence of a cloud of neutral hydrogen gas that has absorbed a very specific wavelength of the quasar's intense light during its multi-billion-year journey to Earth. The sheer density of these lines creates a unique barcode for each quasar, a fingerprint of the precise path its light has taken through the universe. This is more than just a record of obstacles. It is a three-dimensional map of the cosmic web itself. By measuring the redshift of each absorption line, scientists can pinpoint the distance to each hydrogen cloud, building up a tomographic image of the universe's large-scale structure across vast stretches of space and time. The forest is thickest when we look back to the universe's adolescence, a period known as the reionization era. In that ancient time, the first stars and galaxies were switching on, their intense ultraviolet radiation flooding the cosmos and slowly burning away the fog of neutral hydrogen that filled all of space. The Lyman-Alpha forest is the fossilized record of that great clearing, capturing the moment the universe became transparent to light. Pioneering astronomers like James Gunn realized these absorption lines were not just noise to be filtered out, but the primary signal, a direct probe into the tenuous intergalactic medium that contains the majority of the universe's normal atoms. Why does one quasar's spectrum look so different from another's? The answer lies in the unique line of sight. Each beam of light traverses a different cross-section of the cosmic web, passing through regions of varying density and ionization. One path might pierce a dense filament of the web, resulting in a thick, tangled forest of lines. Another might travel through a more tranquil cosmic void, yielding only a few sparse trees. This variation is the key to its power, allowing us to sample the universe's structure in countless different directions. By studying the precise patterns in this forest, cosmologists can trace the subtle influence of dark matter, whose gravitational wells guide the formation of these hydrogen clouds, and even sense the imprint of dark energy, which governs the expansion rate that sets the overall scale of the web. The Lyman-Alpha forest transforms quasars from simple points of light into the most powerful flashlights in the cosmos, illuminating the delicate, invisible architecture that holds everything together. These intricate shadows reveal a universe permeated by structure, a thought that leads us to wonder what happens when the cosmos itself begins to glow. Long before the first stars flickered to life, the cosmos was a sea of pristine hydrogen, a silent era known as the Dark Ages. The only signal from this formative time is a faint, specific whisper, the 21-centimeter line, emitted by the neutral hydrogen atoms that filled all of space. This radiation is our only possible window into that primordial darkness, a direct probe of the universe's condition before any galaxies existed. Projects like the ambitious Square Kilometre Array are being built with this singular goal in mind, to tune their vast electronic ears to this ancient radio hum. Why is this specific wavelength so crucial? It acts as a cosmic thermometer and a map maker. The precise characteristics of the 21-centimeter signal would reveal the temperature and distribution of that early hydrogen, allowing us to chart the subtle ripples that would one day collapse into the first stars and galaxies. It could even show us the moment those first stellar furnaces ignited, their ultraviolet light beginning to burn away the hydrogen fog in the epoch of reionization. The quest to capture this ghostly signal is already underway, with astronomers like Judd Bowman reporting a tantalizing, though deeply controversial, detection that hints at an unexpectedly cold early universe. If confirmed, it would force a dramatic rewrite of our models, perhaps pointing to interactions with exotic dark matter. Detecting the unambiguous 21-centimeter line from the Dark Ages would be like finding a photograph from the universe's infancy, a blurry snapshot from a time we have only ever theorized about. What other primordial secrets are encoded in that faint radio static? This is the next great frontier, a chance to watch the cosmos wake up from its long, dark slumber and begin its journey toward the complexity we see today. This deep look back at the universe's simplest beginning inevitably turns our gaze toward its ultimate, complex end. The universe's final act might not be a silent freeze, but a violent, cosmic shredding. If the mysterious force of dark energy grows stronger over time, its repulsive power would not just push galaxies apart, it would eventually overwhelm every force that holds reality together. This is the Big Rip, a hypothetical doomsday where the fabric of space itself tears everything to pieces. First, galaxy clusters would be ripped apart, then individual galaxies would be pulled from themselves. The final moments would be almost instantaneous. Stars would be torn from their planetary systems, planets would be shredded into dust, and in the last fraction of a second, every atom, every atomic nucleus would be ripped asunder. The cosmos would end as a diffuse, cold fog of fundamental particles, forever isolated and unable to ever interact again. Cosmologists like Robert Caldwell have mapped the mathematics of this terrifying finale, which hinges on a single, unknown number called the equation of state of dark energy. This value, often labeled as W, describes the pressure dark energy exerts. If this number is less than -1, the phantom energy scenario, then a big rip becomes inevitable. The timing of this catastrophe is almost incomprehensibly distant, trillions of years in the future, but its possibility forces us to confront the ultimate fragility of existence. Why would the cosmos be built with such a self-destructive flaw? The Big Rip is just one of several potential endings, standing in stark contrast to the gradual dimming of the Big Freeze or the fiery reversal of the Big Crunch. Each finale depends on the precise balance between dark energy, matter, and the geometry of the universe. Determining which fate is ours is one of cosmology's greatest challenges, a puzzle that requires ever more precise measurements of the universe's expansion and the true nature of that dark, driving force. This ultimate uncertainty reveals that the final chapter of the universal story is not yet written. The cosmos retains its capacity for profound transformation, capable of endings as dramatic and final as its beginning was brilliant and sudden. The delicate fine-tuning of our universe, from the mass of the Higgs boson to the energy of the vacuum, points toward a staggering possibility. What if our cosmos is not unique, but merely one page in an infinite library of realities? This is the Multiverse Hypothesis, a radical solution to the puzzle of why our physical laws seem so perfectly calibrated for life. In this view, we do not live in a special universe. We simply inhabit one of the rare bubbles where the numbers lined up correctly. The constants of nature, like the strength of gravity or the mass of an electron, could be random outcomes different in every cosmic domain. We find ourselves here for the same reason a fish finds itself in water, because an environment with different rules would be utterly inhospitable. Theories like eternal inflation provide a compelling mechanism for this cosmic proliferation. In this model, the rapid expansion of spacetime that occurred after the Big Bang never truly stops everywhere. Instead, new pocket universes are constantly budding off from the inflating background, each one potentially frozen into a different set of physical laws. The string theory landscape offers another pathway, suggesting a vast number of stable solutions, perhaps 10 to the 500, each one representing a different possible universe with its own unique properties. Physicists like Max Tegmark have organized this dizzying concept into levels, from the simplest, where our observable universe is just one of many in an infinite space, to the most abstract, where even the fundamental mathematical equations describing reality are different. This framework transforms the question of why our universe is the way it is. Instead of asking why the laws are life-permitting, we ask why we find ourselves in one of the few life-permitting regions in a much vaster multiverse. It is an explanation that removes the need for a single cosmic architect, replacing it with a principle of sheer, mind-numbing abundance. Yet, for all its explanatory power, the multiverse remains deeply controversial. The central criticism is its testability. If other universes are permanently beyond our causal horizon, forever separated from us by an ever-inflating void, how can we ever gather evidence for their existence? Some scientists propose looking for subtle imprints on our own cosmos, like a bruise from a long-ago collision with another bubble universe, perhaps even the cold spot in the cosmic microwave background. Others suggest that the unique statistical signatures of a multiverse might be encoded in the gravitational waves from the earliest moments of time. Until such evidence is found, the multiverse sits at the precarious boundary between physics and philosophy, a breathtaking idea that challenges the very definition of science. It pushes us to consider that the cosmos, in its ultimate creativity, does not just think differently. It thinks of everything at once, exploring every possible version of reality across an infinite canvas of existence. This expansive vision of infinite possibilities brings our journey to its final, reflective stage. Our journey through 35 cosmic wonders reveals a universe far stranger and more creative than we ever dared to assume. Each phenomenon, from the spooky connection of entangled particles to the chilling possibility of a multiverse, is a testament to a cosmos that operates on a logic all its own. These are not mere anomalies or errors in our calculations. They are fundamental features of a reality that values mystery as much as it does order. They challenge our most basic assumptions about space, time, and our own place in the grand scheme. What does it mean to live in a universe where emptiness actively shapes the cosmos, where time is a personal experience, and where the vacuum of space holds the key to our ultimate fate? These ideas permanently reshape our perspective, transforming the cold, empty void into a dynamic and thinking entity, one that is constantly writing its own rules in a language we are only beginning to decipher. This exploration is a reminder that wonder is our most valuable tool for discovery. If this journey has shifted your view of reality, consider sharing your thoughts on which cosmic mystery amazed you the most. Thank you for joining this voyage into the unknown. Keep looking up and never stop wondering.